Welcome to Brain Vision.
According to Newton's third law, the tug is also being pulled by the asteroid with a force of 490 newtons. Now, we can use Newton's second law on each of them separately to calculate the acceleration of them separately. So, for the asteroid, we have the following. The net force acting on the asteroid is equal to its mass times its acceleration. Let me call it AA for acceleration of the asteroid. Then the net force is equal to 490 newtons, the net force acting on the asteroid only. And this is equal to 6200 times the acceleration of the asteroid. Then the acceleration of the asteroid is equal to 490 divided by 6200. There is a simplification that can be done here. And then we have that the acceleration of the asteroid is equal to 49 divided by 620, which is approximately 0.08 meters per second squared. Then, the position of the asteroid as a function of time is equal to its initial position plus its initial velocity times the time plus its acceleration times the time squared divided by 2. But note that its initial position we can say is equal to 0. So here is 0. Its initial velocity is equal to 0 because it begins at rest. So the only term that is left is the last one. So for the asteroid, we have the following. The asteroid position as a function of time is equal to 0.08 times t squared divided by 2, which results in 0.04 times t squared, and only that. Now, let me organize this information here and do the same thing for the tug. Nice. Now we repeat this calculation for the tug. So for the tug we have the following. The net force acting on the tug is equal to its mass times its acceleration. Let me call it AT. Then, one more thing. Let me define everything that is pointing to the right as things that are pointing towards the positive direction, and everything that is pointing to the left will be pointing to the negative direction as a consequence. Then, the net force that is acting on the tug is equal to minus 490 because it's pointing to the negative direction. And it's equals to 35 double zeros, the mass of the tug, times the acceleration of the tug. Then, the acceleration of the tug is equals to minus 490 divided by 35 double zeros. That is a simplification, and this gives us an acceleration of approximately minus 0.14 meters per second squared. Now, we can calculate the position of the tug as a function of time as follows. The position of the tug as a function of time is equals to its initial position plus its initial velocity times time plus its acceleration times time squared divided by 2. Its initial position is equals to 450. Its initial velocity is equals to 0. Then, the position of the tug as a function of time is equals to 450 minus, because the acceleration is negative, 0.14 t squared divided by 2. And we can solve the second fraction to get the following. 450 minus 0.07 t squared. Now let me organize the board again. Fine. So now we have to solve the meeting. So when they meet, they will be at the same position. So when they meet, SA will be equals to ST. So 0.04 t squared will be equals to 450 minus 0.07 t squared. Now we have to solve for t. We can do this by sending this term to the other side first. So we have 0.04 t squared plus 0.07 t squared being equals to 450. Then 0.11 t squared is equals to 450. So t squared is equals to 450 divided by 0.11, And then t is equals to the square root of 450 divided by 0.11, which is approximately 64 seconds.